We're going to talk about a little bit more about secant lines and tangent lines, and I think this section probably is the kind of the turning point from where we're prepping to talk about calculus, and we are really getting into the calculus part. Limits kind of was the introduction. Continuity brought us a little bit further along. In the last section, we talked about average rate of change, instantaneous rate of change. And that's going to bring us to this concept of the derivative that we're going to get to in this section, which is the most important concept that we cover this semester. So just to recap, this is a little bit of what we talked about last time with secant lines and tangent lines. So the secant line, you can pick any 2 points on a curve and connect those 2 points with a straight line, and that will be a secant line. And we talked about that last time, and secant lines are related to average rate of change. Then what we did is we're starting at this point R, we are coming up to some point S, and that would be the secant line, and we could find the average rate of change between those 2 points. And if we want to get to the instantaneous rate of change, what we do is we bring this point S closer and closer until we get as close as we want to R. And once we can pinpoint what that line would be that goes through R and touches the curve at that one point, and that's all, then we call that the tangent line. And that tangent line gives us the instantaneous rate of change. Okay, so what we're going to do this time and what derivatives are all about are about the tangent lines. And so we're really just extending this idea a little bit farther, and that will kind of propel us forward into the rest of the semester and what we're going to be doing. So the slope of the tangent line. So the tangent line of the graph y equals f of x at some point a comma f of a is the line through this point having this slope. And so you can see this is the same thing that we did last time. This is just the instantaneous rate of change that we did last time. Instantaneous rate of change that we did last time. So if the limit does not exist, then there is no tangent at that point. Now, when do limits not exist? Maybe think about that. Limits, most of the time, they don't exist when there's a point of discontinuity. So that is an important thing to remember. We're going to talk about that a little bit more, though, as we go along. So we won't spend too much time, but that's something to think about. When does a limit not exist? That helps us find where there is no tangent line to the graph. So let's look at an example. So we're going to look at these two ideas together. So the secant line and the tangent line. Find the equation of the secant line through the points where x equals -1 and x equals 1. And we have the equation f of x equals x squared minus x. Now, I'm not going to be using graphs if they're not required on these problems. So in this problem, we don't really need the graph. But when you're doing these on the homework, when you're trying to learn this material, and kind of going forward the rest of the semester, really, it might be a good idea to have the graph as a reference just to kind of visually see what's going on. You want to be able to do this without the graph, but in the beginning, it's probably a good idea to reference the graph. And so once we get this equation, the secant line, maybe get on Desmos, graph this function, graph the secant line, and then see what it looks like. And then once we get the equation of the tangent line here, do the same thing and just see what it looks like. So again, you don't need to know what the graph looks like. So we'll be doing later on probably some functions that you won't be able to just instantly know what they look like. This one probably, I mean, obviously it's a parabola. It's going to look something like that. But where is it on the XY plane? We'd have to figure that out, I guess. But use Desmos or use whatever graphing tool you have, and just to kind of get a picture of what these things look like as we are going through them. But eventually you do want to get to where you're comfortable doing this without a graph, because if you see this problem on the test, you don't have a graphing calculator, so You got to be able to do that, but the graph does help in the beginning. So find the equation of the secant line. That's really just find the average rate of change between these 2 points. So so the equation of the secant line will just be f of -2 minus f of 1 over -2 minus 1. Now, it doesn't matter which point, if I chose this one to be x2, this one to be x1, but it doesn't matter. I'm sure you know that. You can pick whichever one you want. So let's find f of -2. So we get -2 squared minus -2. So that'd be 4 plus 2, which is 6. And then let's find f of 1. That will be 1 squared minus 1, which is 0. So we get 6. And actually, this is not the equation of the tangent line. We're getting the slope of the secant line. Sorry, the equation of the secant line. We're getting the slope of the secant line here, and then we'll get the equation. So the slope of the secant line, is 6 over -3, which is -2. Now, how do you get the equation? Well, the equation of a line, we all know, is y equals mx plus b. And so we know that the slope, so this is the slope, that's going to go right there. And so we have y equals -2x plus b. And so we need to figure out what the b is. Now, the way you figure out what the b is, you plug in one of these ordered pairs. So we have this ordered pair, which is -2, 6. You have this ordered pair, which is 1, 0. So let's just plug in 1, 0, since those numbers seem easier. So plug in 1, 0 for x and y. And we're going to get that b equals 2. So our secant line is y equals -2x plus 2. All right. Now that honestly, that's really just find the equation of the point of the line between 2 points. And we're given that we can find the ordered pair for these points based on the function, but really that's all we're doing. Because it almost doesn't matter what this is as far as what we're doing. Obviously that helps us get the y value, but it doesn't make it, let's look at part B, find the tangent line at x equals -2. So now we need to take the limit as x approaches -2, or actually I think we did, we'll do h, since that was, I think, the formula that we had at the beginning. H approaches 0, f of -2 plus h minus f of -2 over h. And we're going to take the limit as h goes to 0. All right, so we have the limit as h approaches 0. And so now we're going to plug in -2 plus h in for both of the x's. So we have -2 plus h squared minus -2 plus h, and then minus f of -2, which we know f of -2 is 6. So minus 6 all over h. Then we get limit as h approaches 0. Let's FOIL this out. So we get 4 minus 4h plus h squared. Distribute the negative. So plus 2 minus h minus 6. And if you remember from last time, when we do this, any term that does not have h should cancel out. If it doesn't, don't just mark them out, but make sure that they do. So 4 plus 2 minus 6 is 0. So that does cancel out. So we have the limit as h goes to 0 of -5h plus h squared over h. We can factor out an h. We'll just do it like this. So we have limit as h goes to 0, -5 plus h. And so that's going to be -5. So this is the slope of the tangent line. And so now to get the equation of the tangent line through x equals -2, the point where that curve goes through -2, we're going to do the same thing we did here. We start with y equals -5x plus b. We need to figure out what b is. Now we have to plug in the -2, 6, because the tangent line is not going through 1, 0. It's going through negative 2, 6. So in this case, we have to use this point. Plus b, so we get 6 equals 10 plus b, so b is going to be negative 4. And so then our equation is y equals negative 5x minus 4. Okay. All right, so that's how you find the secant line, the equation of the secant line, and the equation of the tangent line. Now, let's see what we have next. Now we're going to define the derivative. So the derivative is, now whenever you see the word derivative, I want you to think slope. So when we talk about the derivative of the function, we are talking about the slope of the function or the rate of change of the function. So the derivative of the function at x is defined as the limit as h approaches 0 of f of x plus h minus f of x over h. Now this hopefully looks very familiar because this is what we just saw. So the derivative is also equivalent to the instantaneous rate of change. And it tells us the slope of the tangent line at a particular point. So the derivative is just the slope at a particular point of a curve, and it's also the instantaneous rate of change. And the definition formula is still the same as the instantaneous rate of change. So let's see what this looks like. We're going to work this out. So this example kind of just gives you the answer. We'll work out how this plays out. So we have this curve f of x equals x squared. We have the tangent line. So the red line is the tangent line going through the point 3, 9. So this notation here is your derivative notation. So we read this. So f prime. So we read that prime. F prime of 3 equals 6. So we could say the derivative of the function f at x equals 3 is 6. Now, the other way to say that is the slope of the tangent line at this point, 3, 9, is 6. So the slope of this red line is 6. Okay, so now how do we find that? So f prime of 3. Let's use this formula that's right up here. So we have the limit as h approaches 0, f of 3 plus h minus f of 3 over h. So we have the limit as h approaches 0. 3 plus h is going to go in for x. So 3 plus h squared minus f of 3, of course, is 9 over h. FOIL this out. We get 9 plus 6h plus h squared minus 9 over h. Let's come up here. We get 6h plus h squared over h. We cancel 1h from each term. That gives us the limit as h goes to 0, is 6 plus h. And that, of course, is 6, which is what they tell us here. So that's how they get that sixth. And all that's telling us that is the slope of the tangent line that goes through this point. If you wanted to find the slope of the tangent line that went through, say, -1, you could do the same thing and you'd get a different number. Of course, you're going to get a negative number here. But that's when we say the derivative, that's what we mean. And with this notation here, we're going to be using this a lot. F prime indicates the derivative. Okay, so let's see what's next. So we had the derivative alternate form. Now, if you were following along last time, you might remember what the alternate form of the instantaneous rate of change, and this is just going to be the same thing. So f limit as x approaches a is some value of x, f of x minus f of a over x minus a. So again, this is just the same thing, derivative, instantaneous rate of change is looking at the slope of the tangent line. Now the equation of the tangent line, if we had the graph y equals f of x, we're going through some point x1, is given by the equation. So y minus f of x1. Now, do you remember, you might remember point slope form of a line that you do in algebra all the time, x minus x1. So point slope form of a line. So we have the slope there, and then the point is x1, y1. This is going to be the same thing. So the point is not x1, y1, it's x1, f of x1. So we have y minus x1. Now, what is the slope? The slope is not, we don't write it as a slope because generally when you use this form, you're talking about a linear function, but this is any function, and we're talking about the tangent line around that function. So when we talk about slope with curves, we talk in terms of the derivative. So f prime of x. So f prime of x, again, this is just the slope at that point, whatever point you're looking at, and then times x minus x1. So same form, we're just kind of changing our notation and we're making it a little bit broader. This really only refers to straight lines, linear functions. This refers to any function. All right, so use the definition of the derivative. So here's the definition of the derivative, or the one that we had earlier. It doesn't matter which one. Find f prime of x for f of x equals 8 over x. So f prime of x equals, now this is a situation where maybe write the definition down each time you start a problem so that you get used to it. Hopefully you got this one fairly well down. So what is f of x plus h? We're going to substitute x plus h in for x. So we have 8 over x plus h minus f of x, which is 8 over x, all over h. Now we have this crazy fraction here. Let's look at this fraction on the top and find a common denominator. So the common denominator would be x times x plus h. So we have x times x plus h on the bottom. We already had the x plus 8, so we need 8x up here, and then we'll go through the whole deal here. This is algebra stuff that you should be fairly well familiar with. So we get limit as h approaches 0, 8x minus 8x, we'll distribute this 8, minus 8h over xh times x plus 8. So we can just join this denominator with this denominator now. So then we get the limit as h approaches 0, negative 8h over xh, x plus h. Cancel out the h's, and we get the limit as h approaches 0 of negative 8 over x times x plus h. We take the limit as h goes to 0, so that's just plugging in 0 for the h, and we get negative 8 over x squared. And so that is the derivative. So now, if you wanted to find the slope of the tangent line, find the slope of the tangent line at, say, x equals 2. Then all you have to do is find f prime of 2. F prime of x is negative 8 over x squared, so this is just negative 8 over 2 squared, which is going to give negative 2. Okay, now I didn't ask us to do that, but that is what you can do after once you find this. Now you can plug in any valid number for x, and that will give you the value of the derivative, or the slope of the tangent line at that point. All right, so let's look at another type of function here. So we have square root of 2x. We're going to do the same thing. So f prime of x. So we have the limit as h approaches 0, f of x plus h minus f of x over h. And so this is the limit as h approaches 0, square root 2 times x plus h minus square root of 2x over h. Now, obviously you can't just plug in 0 for h. So one thing that when you have radicals and you're taking limits, usually a good idea to try is to multiply by the conjugate, or so square root of 2x plus h plus square root 2x on the top and bottom. So you have the limit as h approaches 0. Now FOIL out the top. So it's just all multiplied together. So we have 2x plus h minus 2x. And that'll be all over h times square root of 2x plus h plus square root 2x. We have the limit as h approaches 0, 2x plus 2h minus 2x over h times all this. Now you can multiply out this 2 if you like. It doesn't really matter. No reason not to. So the 2x's cancel out. That leaves a 2h on top with the h here on the bottom. So the h's are going to cancel. So then we have the limit as h approaches 0 of 2 over square root 2x plus h plus square root 2x. Now we can plug in h, and so we are going to get 2 over square root 2x plus square root 2x. Maybe you can see where this is going, but we got a lot of 2, so I don't want to go too fast, skip too many steps. We have 2 over, now square root 2x plus square root 2x is 2 square root 2x. So now the 2's cancel, and we have 1 over square root 2x. And that is our derivative. Okay, so you can see the process is going to be the same. Algebra may be different. The algebra just depends on the function, but once you get this set up, it's just a matter of figuring out a way to evaluate the limit. Once you evaluate the limit, there is your derivative. All right, so we're going to talk about the existence of derivatives in the next one and finish up this section in the next video.